It's hello from West Virginia. Whoa. No, definitely not. But I do have joke of the day, and I know you're ready for it. This one's a really good one, highly appropriate here. So what do you get when you cross an elephant with a kangaroo? What do you get when you cross an elephant with a kangaroo? Well, great big holes all over Australia. I like that one. Okay, we're going to jump our way into solving rational equations, the second part. We've already had one video where we've looked at solving rational equations, but this second part is going to be a little bit more in depth, because the difference between the first part and the second part is this part 2 is going to have variables in the denominator, plus the numerators are going to be a little bit more complicated than the previous one. In the previous video, those numerators only had one term in each one of them. These numerators are going to have a couple of terms in them, and that's going to stretch ourselves a little bit and make the process just a little bit more complicated. Not difficult, but just a little more complicated. So we've got two methods that we can work with in the previous video. These same methods will work again for these rational equations. They're going to be a little bit more complicated with our terms, with our fractions, but both two methods will still work just fine. And remember, that first method says, okay, these are fractions. And so what I'm going to do is retain the fractions. Yes, they're complicated fractions, but they are just fractions. That's all they are. So what I'm going to do is I'm going to say, okay, I know how to add and subtract fractions. I know it takes a common denominator. And so what I'm going to do is get that common denominator, lovingly called the LCD. I'm going to adjust those numerators. And then just like with basic fractions, once I've got the common denominator, once I've adjusted that numerator, I'm going to add the numerators or subtract the numerators depending on what I'm told to do, and I'm going to keep that denominator. Same process here. The only difference is, like I said, those numerators are going to be a little bit more complicated because they have more than one term in them. So when you are subtracting that second numerator, you need to be careful. You're going to subtract the entire second numerator, all of it. So you're going to need to distribute that negative, that subtraction, you're going to distribute it all the way through that second numerator. And then remember, at that point, you will have single fractions here. And when you have those two fractions and they are equivalent to each other, meaning pan balance, if they have the same value and their denominators are the same, you know that means those numerators have got to be the same. So you're going to drop those denominators and you're going to set the numerators equal to each other. When you do that, you will have an equation that's pretty easy to solve. Now, there's one caveat to this. This idea of dropping the denominators, quite frankly, you can drop those denominators way up here, and I'll show you how that works. Could have done it in the previous video, but I like to mention it in this one because this is the one that gets a little bit more complicated, and so dropping those denominators a little bit earlier seems to help. And again, you could do it in the previous one as well. But we have to be careful because, like I said, what we're going to find in these equations are denominators that have variables in them. So we have to be careful about the solution that we get when we put it in that denominator. Is it going to create a problem? Because remember, these are fractions. What can you not have in a fraction? What will make that fraction no longer exist? Yes, a zero in the denominator of a fraction makes your fraction undefined. Undefined means it doesn't even exist. I can't define it. It doesn't exist. We need the fractions to exist. So we need to ensure that whatever solution we come up with, when we plug it into that denominator, it does not create a zero in the denominator. If it does, we have what we call an extraneous root or an extraneous solution. So you must check those answers. It's always a good idea to check your answers to make sure you're right, but in this case, it's critically important to check your answer, because if you plug it into that denominator and it creates a zero in that denominator, an extraneous root, then you don't really have a solution at all. So we've got to be sure that we check our solutions. So that's our first method that retains the fractions and get that common denominator. The second method, remember, gets rid of all the fractions in that first step. We still utilize the LCD, but what we do is we multiply everything, every single term by that LCD. And in one fell swoop, it gets rid of all those fractions. And then we have an equation that is pretty easy to solve, but once again, we need to check our answers for those extraneous roots, for the ones that cause problems. Now, keep in mind, this method always works even if you do not have an equal sign. If you do not have an equation and instead you have an expression, equations have equal sign, expressions do not. So if you don't have an equal sign and it's just an expression, but it still has those fractions in them, this method will work. When you don't have an equal sign in it and it's just an expression, this method will not work. So you've got to keep that straight, which we've talked about before in the previous video. So let's take a look at, I have several examples on this because these are the ones that get to be a bit challenging, and people do have a habit of, a tendency to struggle with these a little bit. So I've got several examples. I've got, as a matter of fact, I've got 2, 4, 6 examples to run through. So in our first one here, actually I think it's 7 examples, but anyways, doesn't matter. I've got lots of examples. So let's take a look at this first one. The idea is get that common denominator. So I'm going to look at my 3z, 5, and 15z. I want the smallest term that all 3 of those will go into. Well, if I look at the 3, the 5, and the 15, all of those 3 numbers will go into a 15. So that's going to be my common denominator here of 15 all the way across for every single term. But notice that these two have z's, so this one needs a z as well. So all of those common denominators are going to be a 15z. So now, just like before, I'm going to say, well, what would it take to turn that 3z into a 15z? I would have to multiply it by 5. And we've discussed before that means multiply my numerator by 5 because 5 over 5 is 1. And when you multiply by 1, do you change value? No, not at all. And here, I'm not trying to change value. I'm just changing looks, that's all. I'm just trying to get that common denominator. So same thing here. I'm going to say, what would I multiply to that 5 to create a 15z? I'd multiply a 3z. And so I'm going to do the same thing up on this numerator, multiply by a 3z. Now this one's already there. I already have that common denominator, so I'm going to keep the 16 as it is. So we've got those common denominators all the way across. I am ready now to adjust. I've already adjusted the numerators, so now I'm going to combine those numerators into a single numerator. 10 minus 3z, well, I can't really put those two together, so they're just going to sit beside each other over one common denominator. And so now at this point, I'm going to say, okay, I have got 2 equivalent fractions. That's what the equal sign means. Pan balance idea, this is what's in this pan, this is what's in this pan. The 2 pans are equal, they're balanced out, and the denominators are the same. So when the denominators are the same, what has absolutely got to be true about these numerators? This 10 minus 3z had better be a what? Yes, 10 minus 3z had better be a 16. If it's anything other than a 16, it's not going to be balanced. If this is a 15 or if this is a 17, is it going to be balanced? No. I'll have a 15 over 15z instead of a 16 over 15z. Or maybe a 17 over 15z instead of a 16 over 15z. So the whole idea here is, okay, let's drop those denominators and let's set them equal to each other. So now I've got an equation that is pretty easy to solve. Notice that all the variables are in this side. So I'm going to slide all the constants to the other side, and that will give me, remember, name tag. Sign in front's the sign that goes. When you go to a meeting, you put your name tag on the front. You don't put your name tag on the back, because I don't know who you are. I need your name tag here on the front so I can identify your face with your name, so I know who you are. So this is a negative 3z. Do not lose that sign. And then over here, 16 minus 10 is 6. Now we know what to do to get that z by itself. I'm going to divide through by a negative 3. And when I divide by a negative 3, I get z equal to a negative 2. So there is my answer. Now, remember, I need to check and say, will this cause a problem when I plug it back in? When I take that negative 2 and I plug it in right here, will it cause a 0 in the denominator? No, not at all. Because 3 times negative 2 is a negative 6. When I plug it in right here, will it cause a problem? No, because 15 times negative 2 is a negative 30. So I know that this is not an extraneous solution. I know this one will be perfectly fine. Now, that second method, remember, second method says I'm going to use that LCD, but I'm going to handle it in a different way. It says I'm going to take my beginning equation of 2 over 3z minus 1/5 equals 16 over 15z. And what I'm going to do with the LCD this time is I'm going to multiply everything by the LCD. Every single term gets multiplied by the 15z. So the first term gets multiplied, the second term gets multiplied, and even in the back it gets multiplied by that LCD. The reason we're doing this is because, remember, we are now multiplying fractions. The x for multiplication means we're going to cancel on those diagonals, we're going to cancel up and down, and then we're going to shoot straight across. So what happens here is when I put that 15z over 1, look at this diagonal, the z's cancel, and 3 goes into 3 once, 3 goes into 15 5 times. Notice what I'm left with right there? Just a 10, that's all, just a 10. So now over here I'm going to do the same idea. I'm going to put my 15z over 1, I'm going to check those diagonals. 5 goes into 5 once, 5 goes into 15 3 times. Notice what I'm left with here is a minus 3z. And in the back, notice that when I put this over a 1, the 15z's completely cancel out. What am I left with? A 16. And notice this is exactly the equation that I had right there. And I can run through and solve that. So you can see that yes, method 1, method 2, that from the previous video, they still work here even when you have variables in the denominator. You just have to be careful about including those variables in your common denominator. Now, it is a good idea to check to make sure that my solution of -2 will work. So let's throw that check in here. And so I'm going to put a -2 in here, giving me 2 over 3 times -2 is a -6 minus 1/5. And on this side, 15 times -2 will be a -30. And so when I get that common denominator all the way across, then that common denominator is going to be a -30 for every one of them. Multiply this by 5, multiply this by 5. -30 here. And multiply this by 6, -6, multiply this by -6. Now notice here, let me fix that. Negative divided, there we go. Because negative divided by negative is going to be a positive. And on this one, I've got a 16 over -30. Here, when I combine these, I basically, remember that negative can sit on the denominator or the numerator. So I'm going to slip it up here to the numerator. And if you need to, call this plus a negative, giving me a -10 over 30 plus a -6 over 30 gives me a -16 over 30, which is exactly what we have over here, because again, that negative can sit on the denominator or the numerator or out front. And if I slip it up there on the numerator, notice I did create truth. I've got the same thing on the left and the right hand sides. So I know that this is the right answer, and more importantly, it's not an extraneous solution, because when I plug it into the denominator, it does not create a 0 in that denominator. So let's try another example, and you know I've got lots because I want you to feel very comfortable with this. Okay, so here we have our second example. Notice in this one, once again, we've got variables in the denominators, but we're still going to utilize method 1 and method 2 to get through it. So method 1 says, okay, I've got a couple of fractions. I'm going to retain the idea that these are fractions. And I might get a common denominator for both of them. What is the smallest number that a 3 and a 5 will go into? Just like before, that's going to be a 15. So I'm going to convert everything to 15ths. And notice that both of them have an x. So I need to keep that x in that denominator. And so I'm going to look at these. I'm going to say, well, what would it take to turn this 3x into a 15x? Certainly I need to multiply by 5. Now here's where it gets kind of tricky. When I multiply the numerator by 5, notice that's a big numerator. It's not just a 2x. It's not just a -2. It's a 2x minus 2. So when I multiply that numerator by 5, I'm multiplying the entire numerator by 5. I like to put a parenthesis around it to remind me, multiply that 5 not just to the 2x, not just to the 2, but to both of them. And when I do, I get a 10x minus 10. Now, similar idea over here. What do I multiply that 5x by to create a 15x? Multiply it by 3. And we know that we got to do that on the numerator. And yet again, it's a pretty big, complicated numerator. So I need to multiply every term by that 3, giving me a 12x minus 18. Now, notice that there's just one fraction here, We're kind of getting to it quick on this one. So if those fractions are equivalent and their denominators are the same, like I've said many times, what has got to be true about these numerators? Yes, they have to be equal to each other. So that 10x minus 10 had better be a 12x minus 18. And now we have an equation that's pretty easy for us to solve. So I'm going to go ahead and subtract 10x. You know that you could subtract the 12x. You know you could add the 10 or add the 18, however you want to start. We're all going to get to the same place, even if you start different than I do. But this gives me a negative 10, because remember, sign in front's a sign that goes. The name tag on that 10 is a negative. Do not rip that name tag off until you've left that meeting. So I'm going to keep that name tag there. 12x minus 10x is 2x minus 18. So I threw all my variables on this side. That means all the constants have got to go to the other side. I'm going to add an 18 here, add an 18 here. That will give me 8 equals 2x. And I think at this point we all know what to do. At this point we're going to divide by 2, and that tells me that my x is going to be a 4. Now once again I need to check, is this going to cause an extraneous solution or an extraneous root? When I put that 4 down here or here, does it cause zeros in the denominator? Absolutely not, because 4 times 3 is 12. 5 times 4 is 20, so that 4 is going to be just fine, no problem. Now let's take a look at the second method. Second method once again says, okay, I'm going to start with my equation of 2x minus 2 over 3x and 4x minus 6 over 5x. And what I'm going to do is take that LCD and just handle it different. I'm going to multiply everything by that LCD of 15x. And remember what that means is multiply this side by the 15x and multiply this side by the 15x. And I want to point out right here that this is the reason that this method is okay to use when you have an equal sign. It's not okay to do when you don't have an equal sign. When there's no equal sign right here, you're going to change value right there. Because when I multiply through, and remember, canceling on those diagonals for multiplying fractions, the x's will cancel, and 3 goes into 3 once, 3 goes into 15 5 times. I will be left with 5 times 2x minus 2, and 5 times 2x minus 2 is 10x minus 10, like we saw right here. So the idea is this, that if there's no equal sign and I try to do this right here, I'm completely changing value. I'm taking what was a 2x minus 2 over 3x, turning it into a 10x minus 10. They do not have the same value. There is no way that a 10x minus 10 has the same value as a 2x minus 2 over 3x. So this method only works when there's an equal sign. When you have expressions with no equal signs, you're stuck with this method 1 up here. You can only, but this method 1 works whether you have an equal sign or whether you don't have an equal sign. It's a good method because it works all the time. But, so I'm going to carry on and I'm going to cancel in this diagonal as well. X's will cancel. 5 goes into 5 once, 5 goes into 15 3 times. So I'm left with, on the right hand side, 3 times 4x minus 6. And we know what to do with this one. We're going to distribute, and when we distribute, like I said, I come up with a 10x minus 10 like you see here. And when I distribute here, I come up with a 12x minus 18 like you see right here. So that'll take me right here, and I'm going to solve that resulting equation, getting once again the x equals 4 in either method that you choose. Now, once again, we can check this. And if we check it, we're going to take that 4, we're going to plug it right up in here. And we'll have 2 times 4 minus 2 over 3 times 4. And on this side, we'll have 4 times 4 minus 6 over 5 times 4. Now 3 times 4 is 12. 2 times 4 is 8. 8 minus 2 is 6, so I have 6/12, which I know simplifies to 1/2. Here, 4 times 4 is 16. 5 times 4 is 20. 16 minus 6 is 10, so I have 10 over 20, which as well simplifies to 1/2. So yes, I did create truth, meaning that is the correct answer. All right, let's try another one. All right, so here's our next example, the third example, and notice that we have very complicated denominators this time. It's not just 3 times x, it's not just a single term, I have 2 terms down there. But life is pretty, well, not super complicated so far, because notice I do have these common denominators here, and this one is going to be very easy to turn into the common denominator. Every one of them I need to turn into an x minus 2. So in this first method where we're going to retain those fractions, what I'm going to do is turn every denominator into that x minus 2, which means I need to take this one and multiply it by an x minus 2 on the denominator and an x minus 2 on that numerator. So I will have 2 over x minus 2 equals x over x minus 2. Now here I'm going to take that negative 2 and basically I'm going to distribute it through. This is where I said you have to be very careful about minusing right here because I am subtracting the entire thing. So a couple of ways of handling it. I can go ahead and just distribute my 2 through right here, giving me a 2x minus 4 over x minus 2. And this is the way most people do it because it's a little bit easier to understand. Or I can distribute a negative 2 through here, giving me a negative 2 plus 4, turning that into a plus sign. Either way is going to be okay because at this point what I'm going to do is I'm going to distribute that negative through, giving me a negative 2x plus 4 and turning it into a plus sign back here. So either way is fine. However, another way of looking at it, and most people really like this, it helps tremendously, and I figured a friend taught this to me just a year ago, and it really eased up a lot of the confusion that my students were having. So at this point, I know eventually I'm going to condense all of this into one fraction, and those denominators are going to be the same, and I'm going to drop the denominators. I know that's where I'm headed. So if that's the case, I could go ahead and drop all the denominators right now. And I could have done that in the previous examples. I could have just gone ahead and dropped all those denominators as soon as I hit the point where I had adjusted the numerators. I could have gone ahead and dropped all the denominators. And that does make life a little bit easier. So let's go ahead and drop them. And that'll give me a 2 equals x minus, now be careful though, minus a 2x minus 4. And quite frankly, I could have dropped it right up here. Now, had I dropped it right up here, what I would have had is minus 2 times x minus 2. And some people really like to do it right there because this whole negative sitting out front like this with that complicated numerator really kind of stresses people out. So a lot of people right here will go ahead and drop it. And that's not a bad idea at all. So I'm going to go ahead and go with that. And again, either way, whether you drop it right here or drop it here, I'm still going to say I need to distribute that negative through, and what I'm going to end up with is 2 equals x minus 2x plus 4, which if I would have distributed my negative here, dropping all these, distribute the negative, I still would have got a negative 2x plus 4. I would have got the same thing, so it's okay. But like I said, a lot of people like to go ahead and drop the denominator pretty quick in it. Because it makes a less stressful situation with forgetting to distribute the negative. At this point, I have an equation that's pretty easy to solve, but I'm going to combine up my like terms first. X minus 2x is a negative x, and so I'll have 2 equals negative x plus 4, and I know what I have to do now is subtract 4 on both sides, giving me 2 minus 4 is a negative 2. Negative 2 equals negative x, and you know to go through and divide by negative x, or just simply change all the signs, giving me x is 2. Now remember, I need to be very careful, and I need to check those denominators. I need to say, okay, if I plug this in, is it going to be an extraneous root? Will it cause problems? If I take a 2 and plug it right in here, 2 minus 2 is 0. It does cause problems. It does create a 0 in the denominator. So when now remember, this is the only solution that works. This is it. That's the only one. X can only be a 2 in order to make the left and the right side be the same. This is the only number that I can plug in here, 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 and make the left side and the right side be the same number. But the only number that works causes a 0 in the denominator, so it can't work. So if that's the case, what is my solution? What can I use? you're right, I can't use anything. So when I can't use anything, quite frankly, I don't have a solution. So my answer to this is going to be no solution. Now, let's go check method 2. Remember, method 2 says I'm going to take my original equation here, my 2 over x minus 2 equal to x over x minus 2, and I'm going to multiply everything by that LCD. The LCD is still going to be my x minus 2, but I'm going to multiply everything by that. So that means I'm going to take my first term, my 2 over x minus 2, I'm going to multiply it by the x minus 2. I'm going to take this term here, x over x minus 2, multiply it by x minus 2, and I'm going to take my last term and multiply it by x minus 2. And the beauty, like we keep seeing, is whenever you multiply fractions, there's that stupid gang symbol again. You cannot escape it. You're going to cancel on those diagonals. So on this diagonal, the x minus 2's will cancel, and I'm left with just a 2. And on this one, yet again, on those diagonals, x minus 2's will cancel. I'm just left with an x. And then right here, nothing cancels, but I'm left with a minus 2 times x minus 2. And you know that when you distribute here, you get minus 2x plus 4, which is exactly what we had right there. And you're just going to keep on trucking with it, getting your x equals 2, but knowing that you need to check that in that denominator. Does it create a problem? Does it create a 0 in the denominator? It does, meaning you've got no solution. Okay, let's try just a few more, because I want you to be really good at this, and lots of examples really help seal it in and make you very confident in your skills. So we've got another one coming. Okay, here's our fourth example, looking very similar to the previous example. And so we know that in that first method, what we want to do is retain the fractions. We want to get a common denominator all the way across. Notice the common denominator is going to be an x plus 4 to make them all the same. So this one is already there. But this one, I need to multiply it by an x plus 4, and I'm going to multiply my numerator by an x plus 4. So minus 7 times x plus 4 over x plus 4. And then on this one, a negative 4 over x plus 4. So, like we said before, at this point, the easiest thing to do, you know you're going to condense this into one single fraction. You're going to distribute a negative 7 through, you're going to combine all those up and keep that denominator, but then eventually you're going to drop the denominators because you're going to say the fractions are equivalent, and if the fractions are equivalent and the denominators are the same, the numerators are going to be the same, so you're going to drop them. You can go ahead and drop them right now to make life easy on yourself because you know where you're headed. You've seen it happen before, so you know that it's going to happen. So I'm going to go ahead and drop those denominators and get 3 minus 7 times x plus 4 equal to negative 4. And now I have an equation that's pretty easy to solve. I know that I'm going to distribute my negative 7 through, giving me negative 7x minus 28. And now I know I need to combine up my like terms. And so I know that 3 minus 28 is a negative 25. Notice that what I'm doing here is I'm keeping the sign in front of that 7x. Name tag. Sign in front's a sign that goes. You keep that name tag on the front. And then I've got a negative 4 over here. I know at this point that what I'm going to do is add a 25 to both sides. And so that will give me a negative 7x equal to a 21. And then I know that at this point I need to go through and I need to divide by negative 7, giving me x equals negative 3. And remember, I need to check and make sure, is this an extraneous root? Will this cause a 0 in the denominator? If I put the negative 3 right here, or here, either one, it's the same denominator, will it cause a 0? Well, negative 3 plus 4 is a 1. So no, it's not going to extraneous root. It's not going to cause a 0 in the denominator. Perfectly fine. Now, let's take our second method. Now remember, the second method says, let's take the equation that we started with, our 3 over x plus 4 minus 7 equal to a negative 4 over x plus 4. And what we're going to do is we're going to take every single term and multiply every single term by that LCD of x plus 4. So that means I'm going to take my first term, 3 over x plus 4. I'm going to multiply it by x plus 4. I'm going to take my second term and multiply it by x plus 4. And even here in the back, my negative 4 over x plus 4, I'm going to multiply it by x plus 4 as well. And like we said before, when you multiply fractions, oh, that gang symbol, oh yeah, I'm going to cancel on those diagonals. So these are going to cancel, and I'm left with a 3. No cancellation needing to happen here because I'm not multiplying fractions. And on the other side of the equal sign, these are going to cancel right here, leaving me with a negative 4. And we know that to solve this equation, just like this one up here, that's sitting right there, I'm going to distribute my negative 7 through, and that will lead me right there, and I can continue on. So yet again, another example of both methods working perfectly fine for this. Now, in order to check, because I still need to check and make sure that this really is the right answer. So I'm going to take that negative 3, put it here. Now 4 plus a negative 3 is 1, so that's a 3 over 1, which is just a 3. So that's 3 minus 7. And on the other side, when I put that negative 3 here, negative 3 plus 4 is still 1. And what is 3 minus 7? Yep, it's a negative 4. So truth was created. I know that that's the right answer. All right, you know I've got a few more examples for you because I want you to see everything you can possibly see, and I want you to be comfortable with stuff. So here comes another one. Okay, here we are. This example says that we're going to use these rational equations to solve the following. We're going to find all the values of x that satisfy these conditions. And the conditions that I'm concerned about are right here. That if I take y sub 1, this is not exponents, this doesn't mean y to the second power. It means y sub 1, y sub 2, meaning first y, second y. Now, I'm not really sure why they didn't say, let's take a w minus a z. I'm not entirely certain. But there are cases when we're talking about the same type of situation or the same type of thing, so they need to have the same variable, and you're talking about the first thing and the second thing, but they're the same type of thing. So anyways, there are situations where you would need a y sub 1 and a y sub 2. But it does not mean y to the second power, nor does it mean y to the first power. It means first y, second y. But the idea here is this is the condition. I want to take the first y, I want to subtract the second y, and when I do, I want to get a negative 4 out of that. So how would we solve that and figure out what x needs to be in order to make that happen? You're right. If y sub 1 is all of this, then I should be able to take all of that and plug it in for y sub 1. If y sub 2 is all of this, I should be able to take all of that and plug it in for y sub 2. Now when I do that substitution, I get y plus 1 over 4 minus x minus 2 over 3 equal to negative 4. This looks like the type of equations that we've been solving. And we can use method 1, we could use method 2. Now, if we do method 1, we're going to retain those fractions, and we're going to get that common denominator, and for the common denominator for all these, 4, 3, and 1, the smallest number they will all go into is a 12. So I'm going to convert everything to 12ths. And if I multiply this by 12, multiply my numerator by 12, giving me a negative 48. If I multiply this by 4 to get a 12, that means multiply this by 4, giving me 4 times x minus 2. And on this one, I need to multiply by 3. Multiplying my numerator by 3 would be 3 times x plus 1. And as we've discussed before, we can go ahead and distribute if we'd like to. Or we could go ahead and drop those denominators right in the beginning. It's okay either way you want to go. I could go ahead and distribute that negative through and call it plus a negative 4x plus 8, and then combine it all up into one single numerator and one single denominator, or at this point just go ahead and drop all those denominators because you're eventually going to do it. If I go ahead and drop, I need to be careful that I'm subtracting the whole thing, all of it. I need to distribute that negative through. And again, that's one of the reasons why people like to go ahead and drop right here, because you tend not to forget that negative. You know you're distributing a negative 4 through there. And here a lot of times people will forget to distribute the negative all the way through. And instead of getting a minus 4x plus 8, they'll get a negative 4x minus 8 because they'll forget to distribute the negative. So decide where you want to drop those denominators in a way that will allow you to make few mistakes. or no mistakes would be better. So anyways, here's what I've got, equal to a negative 48, because we dropped the denominators. And now at this point, what I'm going to do is combine up my like terms. 3x minus 4x is a negative x. And then 3 plus 8 is 11. And at this point, I'm going to subtract that 11. And when I subtract that 11, I get a negative x equal to a negative 59. And when I change all those signs, because that's what dividing by a negative does, I know that my x is going to be a 59. That is the number that when I put it up here and I get a 60 over 4, which is 15, put it up here and I get a 57 over 3, which is 21, and a 15 minus 20, wait, no, 60 over 4 is 15, 57 over 3 is 19, and 15 minus 19 will give me the negative 4 that I wanted. So like I said, method 1 works just fine. Method 2, remember, and I'm just going to erase this because I really don't have enough room for method 2. But method 2 says, let's go ahead and let's keep, let's use that LCD, but remember we're going to use it in a different way. So method 2 says, I'm going to take my equation that I have right here, and I'm going to multiply everything by the LCD. Let's multiply everything by 12. So when I multiply the first term by 12, what's going to happen is, remember, I'm going to cancel on the diagonals. 4 goes into 4 once, 4 goes into 12 3 times, and I get a 3 times x plus 1. When I multiply my second term by 12, remember, once again, what happens is we cancel on the diagonals. 3 goes into 3 once, 3 goes into 12 4 times, giving me a negative 4 times x minus 2. And when I multiply in the back by that 12, I get a negative 48. And we know that when we distribute, we get a 3x plus 3 minus 4x plus 8 equal to a negative 48. And when we combine up these like terms, we get exactly what we had right up here. Negative x plus 11 equals negative 48. And we're going to run with it just like we did before. So these rational equations are helpful for being able to satisfy conditions. Now what we're going to look at is situations where our rational equations, we got to do a little bit extra stuff in order to simplify it, but that's going to be a part of our third video. So hopefully this helps with solving our rational equations. Yes, the denominator is complicated, it sure is, but we didn't have to do anything special to get that common denominator. We just needed to multiply by a single number, making life a little bit easier. But in the third video that I'm about to show you, we're going to have more complicated denominators. Remember, method 1 says retain those fractions, get that common denominator, adjust those numerators. You can drop that denominator right then if you'd like to, or go ahead and add up those numerators, keep the denominator, then drop it, or distribute that negative through the parentheses, keep the denominator, then drop it. But eventually you're going to drop the denominator. You'll have an equation that you can solve. Method 2 says multiply every single term by that LCD. You'll have a pretty easy equation to solve. But in either case, check for those extraneous roots. I need to make sure that I do not have a situation that's going to cause a 0 in the denominator. Hope it helps. Have a great day.